The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. This is Bruce Long with the U.S. Department of Energy's Better Buildings, Better Plants program. I'd like to welcome everyone to this April edition of the Better Plants Buildings webinar series. As you know, in this series, we profile the best practices of Better Buildings, Better Plants Challenge and Alliance partners, as well as other organizations that are working to improve energy efficiency in the United States. Today's webinar, entitled Because Wastewater Matters, will examine decentralized wastewater treatment. As with distributed power generation, decentralized wastewater treatment refers to localized wastewater treatment by a variety of end users. It can include everything from treating gray water, sludge, to cleaning of industrial wastewater containing heavy metals, greases, and chemicals. We'll hear about two partners whose presenters will discuss their experience in implementing water reuse and treatment systems at the partner sites, as well as the benefits that these systems have yielded. However, first we'll receive an overview of market-ready wastewater treatment technologies that can be implemented in buildings, institutions, and manufacturing plants, along with the energy efficiency gains that these technologies can yield. At the very end, we'll wrap up with a question and answer session, and then remind everyone about some upcoming Better Buildings, Better Plants events. So first, let me introduce our first presenters. So before we get started with the presentation, I do want to remind the audience that we will hold questions until near the end of the hour. Please send in your questions through the chat box on your webinar screen, and then we'll get to as many of them as we can. I also want to remind you all that this session will be archived and posted to the web for your reference, probably about 1 week after today's date. Our first panelist is Eric Lohan from Sustainable Water. Eric is the Director of Technology at Sustainable Water and a co-founder of GrayWorks. Previously, Eric worked as a General Manager for Living Machines. Eric has been involved in the process design of over 100 wastewater treatment and water reuse projects. He is the co-author of 6 patents on innovative wastewater treatment technologies, and he's been involved in permitting some of the first decentralized water reuse systems in Portland, San Francisco, San Diego, Atlanta, and other areas of the U.S. His water reuse projects have won awards from the Water Reuse Association twice, the AIA COAT, U.S. Water Alliance, American Council of Engineering Companies, and the Water Environment Federation. Eric, go ahead.
Thanks, Bruce. So we're just going to walk through kind of an overview of decentralized water reuse, and then go through a couple of kind of quick actual examples. So I like to think of water reuse with sort of 3 main axes. There's a variety of different water sources. Some like rainwater, fairly easy to collect. Others, like gray water or wastewater, potentially more difficult to collect and more difficult to treat. Also a variety of reuse applications. Typically, we think about irrigation and toilet flushing, but also makeup water for cooling towers and boilers. And then there's different scales of decentralized water reuse projects as well. So typically, building-based systems are reusing somewhere less than 10,000 gallons of water per day. A multi-building project might be reusing between 10 and 100,000 gallons per day, and I think of district-scale systems at the 100,000 gallon per day to 1 million gallon per day range. Next slide. So this is a map of different water sources, different treatment steps required for those sources to reach a given water reuse application. I've sort of listed these in order of yuck factor, if you will, but also in order of how difficult certain water sources are to treat. There's this kind of 3 stages in that treatment process. Primary treatment process typically includes screenings for any kind of gross solids, some kind of flow equalization to balance flow source. Typically, there's a secondary biological treatment phase to remove dissolved organic constituents that might be in the water. And then finally, depending on the reuse application and water source, there's some kind of tertiary process. Filtration to remove suspended solids, disinfection to remove potential pathogens, and RO to remove potential salts in the water. Obviously, between different reuse applications, there's different levels of treatment. For subsurface irrigation, not much chance of public contact, so a lot less tertiary treatment. For public contact reuse with toilet flushing, vehicle washing, or surface irrigation, greater need for filtration, disinfection, and in some cases, reverse osmosis. Next slide, please. Somewhat similar type of approach for cooling towers and boilers. Obviously, in these types of applications, salts become more paramount, and so the consideration of RO gets greater weight. This was a kind of quick map. There really aren't hard and fast rules, and project by project, water sources need to be evaluated for given reuse applications. Next slide. It's just honing in on wastewater reuse and the kind of different sort of metrics that are looked at in designing a water reuse system. All wastewater reuse systems require some level of BOD removal to remove dissolved organics, some level of TSS removal to remove suspended solids, and typically nitrification to remove ammonia from the wastewater. Beyond that, it's highly dependent on what the source is and what the reuse is. So public health regulations weigh in, and disinfection is required, as mentioned before, for public contact applications. In certain areas, environmental regulations also apply for disposal to the environment, for removal of nitrogen and or phosphorus. But even if you meet both environmental regulations and public health regulations, the water may not be fit for use in certain applications based on cooling equipment, boilers, or soil conditions. And so deionization or RO is required in those situations. Next slide. Rainwater is typically the easiest source to collect on site and to reuse. Certainly from a permitting perspective, typically a 4-step process. Rainwater is collected off of a roof. It goes through a vortex filter to remove solids that are in the water, such as leaves. A smoothing inlet kind of distributes it into the tank or cistern to prevent roiling. Floating intake connected to a submersible pump is used to kind of preferentially take the cleanest water out of the tank, pump it into the building for reuse. There's typically a skimmer outlet on the overflow that allows floating pollen or other floating material to be skimmed out of the cistern during high level conditions. Water that's pumped back into the building may also be filtered and disinfected before reuse. Rainwater is a great source of reuse when it rains in climates that have regular rainfall, or in times of the year when it's regularly raining. Next slide, please. Rainwater reuse is a more reliable source of water throughout the year in most projects. Gray water is defined as water collected from sinks, showers, and laundries inside a building. A particularly good source of water for multifamily residential projects, dorms, barracks, or mixed-use projects. Again, there's typically a multi-step process. Lint and hair are removed in a screening process at the beginning. Biological treatment will remove dissolved organics in the wastewater. By that point in time, filtration is required to remove any residual suspended solids. Some form of disinfection through UV or chlorine is the final step in the process. Next slide, please. We're sort of stepping up now from building-based gray water systems to building-based wastewater systems. And just to give a sort of case study example that all wastewater treatment systems don't need to look like boxes in your basement. This is a project for the SFPC headquarters in downtown San Francisco, treating 100% of the wastewater from about 1,000 employees in a wetland-based treatment process. And Aaron will talk more about the wetland treatment. This process reuses wastewater back into the building for toilet flushing into the building, and also for irrigation around the site. Next slide. So we'll sort of step up in scale again from a kind of wastewater building-based project to a wastewater district scale project. This is a project we completed for Emory University outside of Atlanta a couple years ago. Next slide. This was Emory's water budget for the year. So about 60% of water on campus is used for potable applications, and about 40% of wastewater on site is used for non-potable applications. This is pretty typical of most campuses that we see in the southern portion of the U.S. It's also typical that the split between heating and cooling water use and irrigation is quite pronounced as it is here. Irrigation tends to be one of the more visible uses of water, but typically for a district-based treatment system, heating and cooling make up significantly larger amounts of flow. So in general, there's plenty of sewage, that 60% of domestic use available to treat to meet the non-potable demand. Next slide, please. This is a quick schematic of our treatment system at Emory. Wastewater is harvested from a sewer lateral running through the campus, pumped through primary screens into the moving bed bioreactors. You see at the top of the screen. It then flows through our sort of indoor hydroponic reactors in the greenhouse. These are treatment reactors with plant roots growing inside the water. The plant roots catalyze an ecology of organisms that help degrade nutrients and other constituents in the water. The project wastewater then flows through a series of outdoor hydroponic reactors, through a clarifier and filtration, UV disinfection into a clean water storage tank, where it's pumped throughout the site. Next slide. The treatment system supplies about a mile of purple pipe, pumping reclaimed water to 3 campus cooling towers and the steam plant on campus. A second phase is under construction right now, and that will add about an additional mile, and we'll pick up Emory Hospital and a couple other smaller cooling towers. And there's a third phase already in the works. Next slide. So typically, municipal scale water reuse projects can take up to a decade for planning, permitting, funding, and implementation. Our project at Emory took a little over 2 years, from initial feasibility through construction and commissioning and startup. Next slide. So the engineering and planning of decentralized water reuse is often considered a lot more sexy than the operations, but no less important. I think operations are sort of critical, not just for district scale projects like these, but for building-based systems as well. The Emory WaterHub to date has treated about 150 million gallons of water for reuse. We've offset about 92% of the potable water at their 3 chiller plants, at an overall net reduction in the energy use for water infrastructure on the campus. Next slide. The Emory project, to my knowledge, is the first project of this scale that was funded by a water purchase agreement. So Sustainable Water provides funding for feasibility, engineering, design, construction, commissioning, and operations of wastewater treatment plants. So there was no sort of upfront capital by Emory University for the installation of the system or the operations of the system long term. And Emory has sort of guaranteed savings based on their water usage over time, as municipal prices increase, their savings increase over that period of time as well. Next slide. So I've worked on water reuse projects for almost 20 years now, and I can say that 20 years ago people were not this interested in water reuse. We've been pretty blown away by the level of interest in this project and in others. And I think what's most sort of interesting is that water reuse is of interest not just to water organizations and green or sustainable organizations, but also to the Atlanta Chamber of Commerce and others. That was just a quick recap of kind of basics of decentralized water reuse and two project examples. Thanks.
Hey, thank you very much, Eric. That was a great presentation. I think we've got some questions and we're going to hold them to the end, but now I'm going to introduce our second speaker. Our second speaker, as you can see on the screen, is Stephen Pierrett of Volvo Trucks. Mr. Pierrett has been the environmental manager since 1999 for the New River Valley plant in Dublin, Virginia, the home of Volvo Trucks there. And he has 43 years of environmental experience with EPA and DOD contractors, consulting industry. Over the past 18 years, Mr. Pierrett has managed projects for process wastewater recycling and reuse, certification for both ISO 50001, the energy management standard, and superior energy performance. They were one of the first plants in the U.S. to get certified. And in 2013, he achieved zero landfill status for the plant under his leadership. Mr. Pierrett has a Master of Science in Hazardous Waste Management from Wayne State University, a Master's in Management from the University of Redlands, and a degree in Chemistry from Anderson University. Stephen, take it away.
Thank you. Next slide, please. First of all, I'd like to give you some context on the NRV plant. Our situation it is located about an hour south of Roanoke, between the Blue Ridge and the Appalachian Mountains. The valley is named after the New River, the second or third oldest river in the world. The plant is 1.6 million square feet and paints Volvo and Mack cabs for all North American production, but only assembles the Volvo trucks locally. For purposes of this discussion, I may refer to the plant as the big fish in a little pond, since we were the largest discharger to the regional POTW in the past. Next slide, please. As an overview, we'll examine some of the benefits of the system over the past 10 years, review a couple of water savings projects, describe how the system became a quality and risk management tool for the plant, and discuss an analysis of water savings versus energy savings. Next slide, please. The water management program at NRV began as early as 2004. We used 2004 as a baseline. At that time, we had usage of some 62 million gallons per year. Since then, the average water use has been about 39 million to 40 million gallons per year, and we overall have achieved about 40 to 41% reduction on average. Next slide, please. Cab leak testing is similar to a high-intensity car wash, but from many angles, testing the cab for leaks before it drives off the lot. Reducing water usage by 22% for this process was the first major improvement at the plant in the early 2000s. For that particular testing, it started around 1,100 gallons per truck. We dropped it to 700, or actually had a savings of 700 gallons per truck, and the investment was about $500,000. Next slide, please. This is an introductory slide for the second project. Our basic dual-train wastewater treatment system was the WWT shown in the top left corner of the page. That is on site, wastewater treatment plant. And originally the wastewater system received the processed water from the plant and was then treated for metals by precipitation. The effluent was discharged by permit directly to the local POTW, publicly owned treatment works. And for the remainder of the slide, the original wastewater recycling system was installed in 2006 and upgraded fully in 2015. The original installation was based on nanofiltration and low pressure reverse osmosis, or RO. The system required replacement in 2015 and was converted to an ultrafiltration system with a high pressure RO. Next slide, please. So what are the drivers for something like that? Sitting in an environmental office, how do you pull this off? So what are the drivers that would prompt you to spend hundreds of thousands of dollars on a wastewater reuse system? Sometimes it's a regulatory issue that allows an internal environmental requirement to be fulfilled or achieved when there is a high price tag associated with the change. Sometimes it's said, never waste a good crisis. The launch towards installing a wastewater reuse system was prompted by a foaming issue at the POTW. Generally, the big fish in the little pond gets the first call. From a corporate perspective, the wanted position for manufacturing plants was to achieve reuse of all processed wastewater. In this case, there was an impending investment on the horizon. In the analysis, the question is, could we achieve the Volvo goal and fulfill the regulatory requirement with one investment? Next slide, please. Compared to other industrial sites for environmental sustainability footprint, the plant's process water use is small, probably by comparison to others. For the environmental risk management evaluation, the POTW was also considering additional effluent limits for the region at the time of the surfactant or foaming issue. As such, the scenario for the capital investment was a comparison of whether the plant could double the size of the wastewater treatment facility to address the additional requirements, or could we significantly reduce the discharge rate to the POTW by installing a wastewater reuse system with a lesser investment, basically going offline. The end goal was to eliminate all discharges to the POTW, if possible, although we did maintain a permit for possible discharges. Next slide, please. As I mentioned, we're rather small compared to some manufacturing sites, but we run about 40,000 gallons per day. The influent is primarily from a 10-stage pre-treat system and an electrocoat system for steel cabs. Primarily at this time, that's for the Volvo product. At NRV, the applied technology is a conventional precipitation system for metals, as mentioned before. Next slide, please. Usage points. The original system was installed with the purpose of servicing non-process use points, including a booth water recirculation system for sludge control. At the time, we did not supply reuse water to processes to avoid being the scapegoat for future quality issues. Didn't want any finger pointing going on, so we didn't want to take the brunt of that. So once the paint shop observed that the system was highly reliable and capable of producing high quality, low conductivity water, better than city water, there was a transition to direct half the reused water to the electrocoat system. However, the water quality demands of ECO did increase the discharge rate to the POTW, lessening the efficiency of the RO system somewhat. The non-process systems were receiving high-quality reuse water, and at the same time, less chemistry was required for maintaining those non-process operations. Next slide, please. As I stated, the nanofiltration low-pressure RO system was installed in 2006, but signs of wear and tear over time prompted an upgrade to a new system with ultrafiltration and high-pressure RO in 2015. Storage capacity also was increased to improve the water balance between production and non-production periods. Next slide, please. For the system upgrade, overall, the upgrade improved the capability to meet the needs of the E-coat system by allowing treatment conductivities as listed above. We reduced the solids loading to the ultrafiltration and high-pressure RO system with additional pre-filter systems and added water storage to improve the water balance. Overall, the upgraded system could further reduce the discharge events to the POTW. Next slide, please. These are just a few shots in the next few slides to kind of give you some idea of the hardware involved in the system. We use UV light for bacterial control, cartridge filtration for a pre-filter. Next slide, please. On the left, we have the ultrafiltration system, and on the right, the high-pressure RO system. Next slide, please. As part of the process improvement, we put in a pre-filter system to take out as much of the solids from the E-coat discharge before it went to the wastewater treatment plant to help maintain the conductivity of the overall output of the system. Next slide, please. And as part of that, as we mentioned before, in terms of water balance to address issues that we incurred during sometimes short shutdown periods over a weekend or lengthy ones over a Christmas shutdown, we added some water storage to allow us to hang on to the good water as long as possible and feed it into the plant when the demand was there. Next slide, please. Overall, the system, we continue to pursue a high reuse rate of 93% for processed water. And overall, the pursuit of this goal has allowed us to use this system as a metric for the paint process performance as far as water is concerned, much like a blood test for an ailing patient. Next slide, please. Beyond sustainability, over the past couple of years, we found that the system had added value for evaluating the overall quality of the processed water influent to the wastewater treatment plant on site. Overall, the quality of the wastewater had been impacting the ultrafiltration system, which reduced recycling rates. In addition, a third party developing plans for a paint shop expansion had noted to myself that the chemical treatment for booth water at our plant was one of the most expensive operations that he had reviewed. And that's pretty much across automotive and truck. Since most of the issues were recent, the financial data was retrieved from the booth water contractor, and it was found that the cost per truck had gradually doubled or more over the past few years. And so we compared that contractor's data over the past few years to their early part of the contract, 07-08, and as we show on the next slide, that raised a major red flag for us. You can see on the left, on the bottom in the dark blue, that maybe the cost was a buck, maybe around $1 per truck. That increased up into the 2 and 3 range for our chassis units, and then we started out around $7.50 to $8 for the main paint shop for the truck caps and plastic parts, and that escalated up into the lower teens. So that was definitely a major red flag for us to look further. Next slide, please. Can you back up a slide? I'm sorry. I guess I wanted to add that this discovery alone represented thousands of dollars of excess cost and excess chemistry for treatment, even at the water treatment plant. And over a short time, a new contractor was selected, and they were required to provide monthly performance metrics for the solids mass balance of the system to manage paint over spray removal and booth water management. Although this is a major find for the wastewater treatment plant management system, work continues to improve the reuse rate as other challenges have been presented by the paint shop expansion with additional chillers, air supply houses, and
I think we need the next.
treatment savings for water is approximately $69,000 to $70,000. In contrast, the energy cost for the system is an additional $18,000 per year. But overall, the net savings is $51,000 per year as you look forward. So as you add on a system, you add on a lot of pumps and a lot of electrical use, but there is a water savings associated with that offsets that. Next slide, please. And a couple of years ago, there was an interest whether the system provided any additional benefit to the community or county in terms of energy savings, because on-site costs you some energy to run that program. But for the off-site, for the county and the community, it was determined that there was very little financial savings, maybe upwards of $100 per year, but we calculated that to be about $70 per year. Next slide, please. So this is, in essence, the same slide as we started with, but just reaffirming that these things have been a benefit to, there have been benefits to a wastewater reuse system at the plant. Overall, the benefits have been considerable for the plant, and some major benefits and value added have been over an extended period. In summary, some of these recent developments continue to compensate for the capital investments and ongoing cost of operation of the system. We are at the end of this presentation, and I just want to thank you for your time and attention. Next slide.
Great. Well, thanks a lot, Stephen. That was a nice presentation and a good example of how a manufacturer can reuse water. I like also the benefit to the community. It's not overload. One of the things that wants to be emphasized that the type of wastewater that would get sent to the public treatment works is a little different. So now they can focus more on the BOD, biological oxygen demand, and if they have anaerobic digestion, they can generate more biogas. I'll go ahead and introduce our last speaker for this afternoon. Ms. Erin English from Biohabitats. Ms. English brings 15 years of engineering expertise to her work in innovative water master planning, wastewater treatment, stormwater treatment, and water reuse projects. She leverages her educational background in chemical engineering for advanced ecological wastewater process design and innovation. As a senior engineer with Biohabitats, a firm focused on ecological restoration, conservation planning, and regenerative design, she applies ecological justice and resilient water design to her ongoing daily engineering practice. Her experience includes numerous landmark high-performance building projects that prioritize water reuse, including Living Building Challenge, Net Zero Water, Sustainable Sites Initiative, and various LEED projects. Her portfolio includes wastewater treatment and reuse systems of various scales at Houslow on 8th in Oregon, the Sidwell Friends School in D.C., the Boy Scouts of America's Bechtel Summit Reserve in West Virginia, and the Omega Institute Center for Sustainable Living in New York. I think Erin's going to focus on the Sidwell Friends School project today. So Erin, please go ahead.
Great, thank you. Hello, everybody. Go ahead to the next slide. So I'm going to focus the bit of time I have here for the presentation today on a reflection on a project that we've had in operation for 10 years at the Sidwell Friends School in Washington, D.C. And I'm mostly going to focus on some of the softer aspects of wastewater treatment and water reuse and the idea of integrating these systems into the landscape. This complements the more technical aspects of the Volvo presentation and that from Sustainable Water. So go ahead to the next slide there. So at the Sidwell Friends School, there are 3 water systems at work within the courtyard of the middle school. This includes on the upper terraces of part of the landscape a wastewater system component, a stormwater bioretention rain garden, and then at the bottom of the hill a biology study pond. Even though all 3 of these appear to be contiguous, they are not necessarily directly connected to one another. You can go ahead to the next slide. But they appear to be relatively seamless and form part of the landscape. So this particular project was a very integrated design. It was the outcome of an integrated design project with a big team of architects and landscape architects and engineers that I've listed here. It was also a very award-winning project, one of the first LEED Platinum schools. It was an AIA Committee on the Environment Top 10 and a U.S. Department of Education Green Ribbon School, among many others. So pretty landmark project. And go ahead to the next slide. The project itself was to basically expand and renovate an existing middle school at the Sidwell Friends School near Washington, D.C. Several hundred middle schoolers attend school inside this building. The wastewater design flow was approximately 3,000 gallons per day. So this is a relatively small project in comparison to some of the others we've seen today. One of the main goals was to provide treatment and reuse for toilet flushing to reduce the building's potable water demand, but also, and arguably as importantly, to showcase from an educational and an immersion perspective what is possible with ecological design and ecological engineering, particularly you know, for children and for their interpretation. You can go ahead to the next slide. So I'll walk you a little bit through what's happening here. We have a multi-stage treatment system that begins with a primary treatment tank, which is a glorified septic tank, which is basically out in the front of the building underground. All of the wastewater from the building is routed to that tank. It has an overflow to the sanitary sewer so that if the system has to be taken offline or for maintenance or whatever, then the water can passively flow to the sewer. So we basically have decentralized the wastewater treatment, but we've maintained our connectivity to the grid, if you will. Go to the next slide. After the primary treatment tank, we come into a series of constructed wetlands, which are on those 3 uppermost terraces. And those are subsurface flow wetlands. All of the wastewater remains under the gravel and is spending about 2 to 3 days in those wetland cells, being slowly degraded and treated by the plants and the roots and the beneficial bacteria living in there. You can walk right across the surface of those gravel wetlands with no problem. So there's no exposed wastewater here. Go ahead to the next slide. After that, we recycle back through a trickling filter, which is sitting on that uppermost terrace there. It's a little tower. That's basically like a shower head over a bunch of media inside of the filter that helps provide nitrogen treatment. As you will see at the end, we have a lot of nitrogen in this system. Go ahead to the next slide. We do polishing with an open bed recirculating sand filter, which is located under the walkway. This provides a high level of clarity and reduces any odor and turbidity in the water. Go ahead to the next slide. And then finally in the basement, out of sight here, is a filtration and disinfection system using high levels of filtration and UV disinfection. We go down to about 1 micron for filtration here. And then the water is reused for the toilets. Any water that's unused is just discharged clean back to the sanitary sewer. Go ahead to the next slide. So the system, that's just a very quick overview right there of what I just walked you through. But the idea is that it's a multi-stage system using all very low-tech, low-energy, low-sludge processes that allow the heart of the system, which are the wetlands and the trickling filter, to be exposed within the landscape as a teaching tool. Go ahead to the next slide. So just some shots. There's a really interesting thing that happens here with the seasonality and the feeling of being surrounded by water. This is a springtime shot. Go ahead to the next slide. So students who are walking on these pathways and who are accessing the site, this is one of the main entrances to the building, are seeing the system over time in different seasons. And it's maintained, like a piece of landscaping, like a garden. And so we don't try to use just tropical plants. This doesn't require greenhouse. These systems are very much open and connected to nature, and you get the sense of the seasonality of it by experiencing it throughout the school year. Go ahead to the next slide. The biology study pond is not connected to the wastewater treatment system, but it is part of the stormwater system and also part of a recirculating pond and stream feature. So we did incorporate some biological treatment into this system, and it recirculates water as you walk by. Students are able to come down and sample and touch the water. And then when it rains a lot, it can basically overflow into the adjacent rain garden. Go ahead to the next slide there. These are some images of the wastewater system components themselves, which again are not connected to the biology study pond or the rain garden, but are immediately adjacent to it. So it's seamless in its form, and this idea of being surrounded by water. So over time, we have worked with the school to help them, experiment with different plant species, flowering species, treatment types of plants. The plant species we focus on are those which are known to provide high levels of robustness in wastewater treatment, cattails and bulrush, but we've also been working with them on, ornamentals and some other flowering species. Go ahead to the next slide. Wanted to say a little bit about the education and the interpretation aspects of the project. Obviously, for a school like this to invest in this kind of landscape, they had multiple reasons for doing it. Treating wastewater is certainly one of them, but providing opportunities to get closer to nature and to wildness for the students in an urban setting, to give them a place to actually come and study and learn hands-on. They have a robust science program here for the middle schoolers, and so teachers are bringing students out. They're doing sampling. They're engaging with the infrastructure systems, and that is very much part of the active learning. So this wastewater and stormwater and water infrastructure, the pond itself also, basically replace what might have otherwise been a more conventional landscape. And so you're trading this idea of the working, you're trading in the idea of the working ecological landscape as a teaching tool, as it's really a beautiful space. And so having that, I think, was a big part of the motivator for folks. You can go to the next slide. They also have an active building dashboard system that shows energy use of the building. The building has all sorts of innovative energy systems, which I'm not touching on here per se today. And then water use, and you can track how much potable water is being saved and how much water is being reused, and how much wastewater is being generated. There's a display in the school for this that's touch screen that the students can use, and there's also access online. I had a quote I just wanted to read also about this interpretation and education part from one of the teachers there, who's called Margaret Pennock. She's a middle school science teacher. And what she told us was that, quote, "The wetlands highlight two central goals of the green building: to create habitat on our urban campus and to reduce the nutrient pollution our school contributes to the Chesapeake Bay watershed." We asked the students why they think our school made the effort to build the wetland system when our wastewater would otherwise go to the Blue Plains sewage treatment plant, one of the best in the country. Once they understand the nitrogen and phosphorus cycles, these cycles are on display every time they step outside, and they understand in a very concrete way how their actions affect the environment, end quote. Go ahead to the next slide. The other thing that has happened at Sidwell over time are extensive tours and opportunities to influence policymakers and regulators. And so there's been a number of groups, obviously, that come through. You can see some of the people on the upper terraces there. You can actually kind of walk into the system and experience it. And so this has also been a good general thing for all of the people who are in the wastewater decentralized realm in terms of being able to show off these kinds of systems. Go ahead to the next slide. We've also included some interpretive signage in creative ways. We wrapped the trickling filter with a flow chart essentially that shows visitors and students what's happening in the system. That's located right up at the top of the site. Go ahead to the next slide. And then finally, just in closing, I did want to say a few words about the operations and maintenance of the system. We've had the opportunity to work closely with Sidwell Friends School and their facilities staff and with the local operator. Inside the trickling filter there, actually on the top of it, is one of our staff who has had the opportunity to take care of this system alongside the client for the last 10 years. That's Olin Christie, one of our engineering techs. And basically, we've provided assistance to the school in a periodic, check-in a few times a year to just do preventative maintenance and ensure that operations are proceeding smoothly. But they do have, their own operators, and we help them, since this is a relatively unique system, we help them with, all of the things to make sure that it's moving smoothly. You can go to the next slide. A few very quick lessons learned. From a water quality perspective, there's certainly, on both of these slides, particularly the lower chart there, there's an immense amount of nitrogen that is generated from schools like this. And so we had designed the system to be able to treat that nitrogen and bring it back through the toilets and remove the rest of the nitrogen on its way through. And so we've definitely seen, much higher levels than, you would normally expect in residential wastewater. And so all of this learning has been applied, to future systems. We've built many, many systems since this one, but this is just an example of like the kind of benefit even us as engineers get with these kind of long-term relationships with the clients and the operators, is to be able to learn from the work and see what needs to be adjusted and how things perform over time. So that's pretty much the bulk of the information that I wanted to present, and so thank you very much.
Okay, if we can get to the next slide, I just wanted to provide some additional resources right here. And while you guys are looking at those, I'm going to start teeing up some questions for our panelists. The first question for Eric, dealing with the WATERHUB, the question is, what is the minimum amount of water use cost needed to offset the financial hurdles of self-funding? They realize that the rate will have a huge impact. Go ahead.
Sure. So we've typically found that somewhere around 50,000 gallons per day at about $10 per 1,000 gallons combined rate for water and sewer. So that's about the U.S. average. And we typically found that somewhere around 50,000 gallons per day of wastewater produced, and need for reclaimed water is typically the threshold for that self-funding. But I'll say that we're actually now looking at a few sort of decentralized greywater systems for urban reuse projects and other kind of smaller scale projects as well.
Excellent. A little bit of a follow-up question for you, Eric. How many buildings or square footage did the EMORY WaterHub serve, and how much did this district scale project cost?
So it serves somewhere around 3 to 3.5 million square feet. I don't know how many buildings that is, but dozens of buildings. Total project cost, all in for engineering, construction, commissioning, was somewhere around $10 million. We've got projects now generally ranging somewhere between $3 and $30 million in terms of kind of total project cost.
Okay, great, excellent. Got a question for Stephen right here. Somebody asked who makes the cartridge filter system, and if you can't answer that, can you answer why is it a separate system than the ECO filter?
Yeah, ProChem is located in Southwest Virginia, and they actually installed the system for us, and they actually put together the nanofiltration system. Some of the materials they use are for the UF unit, or what they call a pan UF membrane, and some of the systems also have a ceramic or PVDF membrane when necessary. For the E-coat, we pull that separately to another filter because it's the material, the resins and such that go into the electric coat are somewhat harder to process, so we try to pre-filter that out for the larger particles anyway, and pull that aside, filter it, and then put it back into the wastewater treatment system as part of that batch. But it's really just to protect and ensure protection for the nanofilters, or the UF filter in this case, ultrafiltration, and to extend the life of the system by pre-filtering that.
Okay, excellent. Thank you. Got a question here for Aaron. The questioner said that their understanding is that the District of Columbia would not allow the treated water to be used as potable water, but that the students actually tested the water treated on site and also tested DC tap water and found that the on-site water was cleaner. Was this true?
Yeah, so that's a question I haven't heard, but two parts to that. So the system is treating all of the wastewater generated by the building, and it's treating it to non-potable standards, to a standard that is suitable for toilet flushing reuse, and they would also be suitable for landscape irrigation. We did not try to, nor did we desire to meet a potable water standard to drink that recycled wastewater. At this scale, that's not really something that's very appropriate to do. I would be surprised if they found that the on-site water was cleaner than DC water, because I do know that the on-site water still has some remnants of nitrogen in it, and it has some remnants of salt. So I don't think it's true that the on-site water was cleaner than DC potable water, though if you held them up next to one another, they would look very similar to the eye.
Okay, so that was a rumor then. Okay, great. Another quick question for Eric. What were the keys to a short feasibility to completion timeline for the EMORY project? How can other people learn from the EMORY projects going faster? Or to get the EMORY project going faster?
Yeah, so excellent question. I think early engagement with regulators, Georgia EPD and the Municipal Water Authority, I think we're sort of key to that. Bringing them in early in the process and making them participants in it, and gaining their valuable feedback. I think was sort of critical. I think knowledge, coming in ahead of time with solid knowledge of the water reuse requirements for the heating and cooling system was essential. And then, from a practical implementation perspective, working in a design-build process also significantly, sped up that timeline.
Okay, excellent. Thanks. Another question here for Stephen. The questioner asked, your filtration steps have a reject stream in terms of concentrate, and he's wondering if that concentrate does go to the publicly owned treatment works or sewer, and is your loading to the PODW smaller volume but more concentrated?
Well, everything that we remove meets the permit limits, so that's always verified before we discharge to the PODW. We do concentrate that for some materials in the waste stream, but I guess at the end of the day, the simple answer is we discharge within the permit limits.
Okay, great, thanks. Another quick question for Aaron. Since the source of your water is the water from sinks and showers, why are the nitrogen levels so much higher than you expected?
Yeah, so this is an interesting question. So the wastewater we're treating from Sidwell is all of the wastewater generated by the school. So that's toilets, sinks, showers, janitor sinks, etc. It's the full wastewater itself, not just gray water. And as part of that, what we have found, and I know Sustainable Water is working on this too, is that as buildings become more and more water efficient, as we get better at water efficiency essentially, what that means is that the concentration of pollutants go up. So in a day use setting like the Sidwell Friends School, you know, it's mostly urine and so and with very water efficient fixtures, and so you get higher concentrations. We anticipated that, but also there have been spikes that were probably beyond typical anticipation, like numbers that are in the 200 and plus, you know, and over milligrams per liter of nitrogen. That's very high. And so this is a challenge for all people considering doing on-site wastewater reuse systems in the context of high-performance buildings that incorporate waterless urinals or, you know, low flush fixtures. Is that you just have to adapt your systems to address that higher loading rate basically, and it's doable. It's just you have to make sure that it's planned for.
Great. Thanks very much. Another question for Eric, also related to the Emory University project. During the commissioning, what was the startup like? If something didn't work as planned, was there a backstop or contingency for you?
Yeah, excellent question. So the I should have made the point that, you know, our non-potable source is always one source to their heating and cooling applications. So they always have a potable source, and so if for any reason we're not able to meet demand at a cooling tower, the potable water valve kicks on and makes up that water. So it's a system that sort of fails open. If there's a problem with the wastewater treatment process, then we turn off our sewer mining pumps, and all the sewage that was flowing by us, you know, continues on down to the treatment plant. That said, you know, it is a complex system. It does have miles worth of pipe, and there is a very real commissioning process. We brought the systems on in phases, you know, starting with the biological treatment plant, commissioned it over a period of a couple of months. When it was producing water to desired levels, then we turned on the first cooling tower, and then, you know, gradually brought the whole system online.
Okay, excellent, thanks. I'll take one more question here for Stephen, and this may be something that Eric or Aaron, if you feel inclined to answer, you may do so. The question is, is LED technology being used in the UV disinfection systems? I don't know, I couldn't remember if y'all had that in your presentation, but I've heard that UV disinfection systems may at some point be able to use LED technology. So Stephen, if you want to answer it, go ahead. Aaron?
Yeah, we're not using it at this time. It's a fairly recent development at the 254 for a wavelength, but I have read where it's being developed, and it's, I guess, on the cusp of being commercially available. Sounds like it would be rather expensive.
Yeah. Okay. Eric or Aaron, any thoughts on that?
Yes, there definitely are commercial ready systems now. I can't speak to their price point, but there are very significant energy savings.
All right. Well, I think that's going to bring us right up to the 4 p.m. mark. So I'd like to close and thank our panelists very much for taking the time to be with us today. Feel free to contact our presenters directly with additional questions. I think on the last slide you should be seeing their contact information. And if you weren't able to get to the questions during the Q&A period, you will receive an email notice when the archive of the session is available online. Also, I'll make a shameless plug for our Better Building Summit coming up May 15th through 17th. If you haven't registered yet, please go ahead. You can see the link right there. And this concludes today's webinar and the season's webinar series. I'd like to invite you to join us in the fall for another engaging lineup of webinars. Thank you very much.